Okay, so let's take a look at Bronsted and Lowry, acids and bases, and how we can predict reactions. So that's what Bronsted and Lowry helps us do, is predict reactions. So the first part is just going over how an acid reacts, and this is based on this theory that an acid is a substance that can donate a proton. So like our strong acid here gives up a hydrogen to water, forming hydronium and that negative ion. So anytime you are donating, you are an acid. Base theory, on the other hand, is a substance that can accept a proton. So example here, we have a hydrogen coming from the water going to the base, forming NH4 positive and the OH ion, which would make it basic. So when we're taking a look at those two reactions, they're reacting with water, and up to this point, that's what we have talked about with Arrhenius' theory. But sometimes instead of having water, we can have it react with each other. So when we're figuring out how to react an acid with a base, these are the steps that we're going to follow. So your first step, list everything that is present and break apart what we can. So you break apart your ionic soluble compounds, you break apart with strong acids, so anything above that gray line in your data booklet. But this time, instead of writing an acid when you break it up and we say it's hydrogen positive present and Cl negative, instead of writing hydrogen positive, write down hydronium, because from before we've talked about how hydrogen positive is so small that it binds to water really easy, and that's gives us hydronium, and that's what gives our products those acidic characteristics. There's a reminder of what stays together, so solids, liquids, and gases, weak acids, so anything that's below the gray line, molecular compounds, and polyatomic species. So when we're going through this, then the next step is to look at your data booklet and all of your acids. So this is, if you're in Alberta, this would be page 8-9 of your data booklet. Your acids are on the left-hand side, your bases are on the right-hand side. And once you've identified all your acids and bases, then you want to identify your strongest acid and your strongest base. So your strongest acid is the highest on the left-hand side of your acids column. Your strongest base is on the lowest from the right-hand side of your bases column. The strongest acid and the strongest base are what's going to react. So then we can show that reaction by showing your acid giving up its hydrogen to its base. We could also figure out your conjugate acid-base pairs from the equation. And the last thing we do is predict what's being favored at equilibrium based on placement on your table. So if your acid is higher up on the table than your base, your products are favored. If your base is above the acid, then if your acid is lower and your base is higher, your reactants are being favored. If you do have a strong acid, meaning we're adding in hydronium, or a strong base, so OH negative is present, then you are not in equilibrium. Nothing would be favored because everything would be products. So let's look at our first example. We have a solution of sodium nitrate. So we're going to break that apart, Na positive and NO3 negative, and potassium hydrogen carbonate. So potassium is K positive, hydrogen carbonate would be a polyatomic ion. And you have a solution, which means this is in water, so water would also be present. So going through this, you wouldn't find Na positive or K positive on your table, but you do see NO3 negative as a base. You see HCO3 negative as an acid and as a base, and you see water as an acid and as a base. So when you're looking at your acids column, you'll see that HCO3 negative is the strongest acid. And when you look at your bases column, you'll see that HCO3 negative is also your strongest base. So it can act as both. That type of species is called an amphiprotic species. So now when we're writing this down, we know that you're going to have HCO3 negative react with HCO3 negative. They're both weak, so our arrow would go in both directions. If it was one of those strong elements, or species, your arrow just goes to the right. Now, one of these compounds have to act as an acid, one needs to act as a base. So the acid will donate its hydrogen to the base. When this hydrogen leaves, you'll end up with CO3, and it will it will lose a positive charge, so you're getting more negative, so -2, plus When the base gains another hydrogen, it will then have 2, and it's bringing with a positive charge, so you're going to become more positive. So this is H2CO3. Now, this is our predicted reaction. Your acid-base conjugate pairs, this would be a conjugate pair, difference of 1 hydrogen, and HCO3 negative with H2CO3, that would be another acid-base conjugate pair. And then lastly, predicting based on the table, your base, HCO3 negative, is higher on the table than your acid. So if your base is above your acid, that would mean your reactants are favored. So that is how we predict using Bronsted and Lowry. I hope you found this helpful. If you did, please like and subscribe. And if you want me to show any other examples, please just let me know in the comments. Thanks for watching.